Hey guys, I am going to read to you Marking Period 4, week of May 25th, Part 1, Regents Review Book Assignment, starting on page 99, technically 100. Insulation and the seasons. Now while I read, I'm also going to be underlining important information and making some text annotations. Topic overview. Without energy from the sun, conditions on Earth would be drastically different. Energy from the sun drives global wind patterns, ocean currents, and the water cycle. Life processes of plants and animals also depend almost entirely on energy from the sun. Without solar energy, Earth would be a frozen wasteland, as all water and all gases of Earth's atmosphere would exist only in the solid state. There would be no life and no rock cycle as it is now known. Very little weathering and erosion would occur. Both Earth and its moon would be almost totally dark. Solar radiation and insolation. A body of matter that is not an absolute zero emits electromagnetic energy. This energy is radiated over a portion of the electromagnetic spectrum, with more of the energy radiated at some wavelengths than at others. The rate of which energy is radiated is called the intensity of radiation. In general, the higher the temperature of a body of matter, the shorter the wavelength. I'm going to jot that down. Higher temp, shorter wavelength. At which the maximum intensity of radiation occurs. At the sun's temperature, the maximum intensity of radiation occurs in the range of visible wavelengths of electromagnetic energy. Insolation, incoming solar radiation, is the portion of the sun's output of electromagnetic radiation that is received by Earth at the outmost part of our atmosphere. The intensity of insolation is the relative strength of the sun's radiation that reaches a specific area of Earth in a specific amount of time. Figure 6.1 shows how the intensity of insolation varies with the wavelength. The maximum intensity of insolation occurs in the range of wavelengths of visible light. However, approximately 48% of the total energy received at the outermost part of our atmosphere is infrared, a type of long-wave radiation. The effects of Earth's atmosphere on insolation. The insolation reaching Earth's surface is different from the insolation entering Earth's upper atmosphere, as shown in figure 6.1. Since the atmosphere is mostly transparent to visible light, it transmits most of the visible light from the sun. However, insolation may be absorbed, reflected, or scattered before reaching Earth's surface. The atmosphere affects insolation in several ways, as summarized in figure 6.3. Absorption of ultraviolet and infrared. Most incoming ultraviolet radiation and other short-wave radiation are absorbed by Earth's atmosphere. Nearly all ultraviolet radiation is absorbed in Earth's upper atmosphere, the stratosphere, by ozone, a form of oxygen gas. In recent years, the amount of ozone in the upper atmosphere has been reduced by the chlorine and fluorine that have escaped into the atmosphere, mostly due to human activities. The result is that more ultraviolet radiation has been reaching Earth's surface. Ultraviolet radiation can be lethal to many forms of life and is a direct cause of skin cancer in humans. Regions in which the amount of ozone has been greatly reduced, popularly called ozone holes, occurs near Earth's poles, especially the South Pole. Other gases found in the atmosphere can absorb long-wave infrared radiation. Water vapor, carbon dioxide, and methane are 3 gases that absorb much incoming infrared radiation. Reflection and scattering. When clouds are present, much of the incident or incoming solar radiation is reflected back into space. However, some of it, including some visible light, is reflected to the atmosphere or toward Earth's surface. Random reflection or scattering of insolation is caused by aerosols, finely dispersed solids and liquids suspended in the air. Besides ice crystals and water droplets, the dispersed materials include dust, bacteria, meteor fragments, volcanic ash, and various other air pollutants. As the concentration of aerosols increases, the scattering of insolation also increases. thus reducing the amount of insolation that reaches Earth's surface. Balance of energy from insolation and Earth's surface radiation. About half of the insolation that strikes Earth's atmosphere reaches Earth's land and water surfaces, as shown in Figure 6.3. Some of the insolation is reflected and some is absorbed. Insolation that is absorbed by Earth's surface is partly converted to heat and tends to raise the temperature of the surface. However, Earth's surface also radiates electromagnetic energy, thus tending to lower its temperature. Over time, the amount of energy absorbed from insolation is generally equal to Earth's surface radiation, and thus temperature and heat are balanced. Factors affecting absorption and reflection of insolation. When insolation reaches Earth's surface, many factors affect whether it is absorbed or reflected. These factors include the angle at which the insolation reaches Earth's surface, the characteristics of the surface, and how the energy of insolation interacts with the Earth's surface materials and living things. Angle of incidence. One important factor affecting the absorption of insolation is the angle at which the insolation strikes the Earth's surface, called the angle of incidence. The altitude of the sun, which varies with time of day, latitude, and season, determines the angle of incidence. The higher the sun in the sky, the higher the angle of incidence, and the more insolation is absorbed. Generally, a lower angle of incidence means the more insolation is reflected and less absorbed. Surface characteristics. Texture and color are also affect the absorption of insolation by Earth's surfaces. When a surface has a rough or uneven texture, more insolation is absorbed and less is reflected. Surfaces with darker colors tend to absorb more insolation than they reflect. Surfaces with lighter colors tend to reflect more insolation than they absorb. For example, ice and snow reflect almost all of the insolation that strikes them. This is one reason the polar regions stay cool even during summer's 6 months of continuous sunshine. Change of state and transpiration. When energy from insolation reaches Earth's surfaces, it interacts with the materials and living things found there. For example, energy from insolation can cause water to change state, melting of ice or snow into liquid water or evaporating liquid water to form water vapor. Energy from insolation also fuels plant growth and increases transpiration, a process by which plants release water vapor into the atmosphere as part of their life functions. When energy from insolation is involved in a change of state and transpiration, it is not available to raise the temperature of Earth's surface. Instead, it is transformed into potential energy. Land and water heating. With equal amounts of insolation, an area of Earth's surface made up of liquid water will heat up and cool off more slowly than an equal area of land. So, water temp changes more slowly than land temp. These rates of heating and cooling differ for the following reasons. Water has a much higher specific heat than the rocks and soil that make up land. Water is highly transparent to insolation. Some insolation penetrates up to 300 feet in clear water, but usually less than a foot in rocks and soil. Rocks and soil heat rapidly because the energy of insolation is concentrated in a thin zone. Water can flow freely, so convection can occur. Convection currents in water can distribute absorbed energy through a large volume. When insolation strikes water surfaces, much of the energy is converted to stored heat as some water evaporates. Thus, less energy is available to increase the water temperature. The greenhouse effect. Although Earth's atmosphere allows much insolation to pass through Earth's surface, most of the radiation from Earth's surface does not escape into outer space. Instead, it is absorbed by the atmosphere. This occurs because Earth's surface radiation consists mostly of long infrared radiation, which can be absorbed by carbon dioxide, water vapor, methane, and other gases in the atmosphere. These gases are called greenhouse gases. The absorption warms the atmosphere and causes it to act as a heat blanket. This blanket reduces energy loss to outer space and makes Earth's surface about 59 degrees Fahrenheit warmer than it would otherwise be. Without any greenhouse gases, the average temperature of Earth would be about 0 degrees Fahrenheit. Figure 6.4 models the process by which the atmosphere transmits shortwave radiation from insulation and absorbs long-wave radiation called the greenhouse effect. In recent years, there have been a major concern that an increased greenhouse effect is causing a type of climate called global warming. An increase in average Earth temperatures. The burning of wood and fossil fuels releases additional carbon dioxide and other greenhouse gases into the atmosphere. This increase in carbon dioxide and other greenhouse gases is thought to intensify the greenhouse effect, thus raising Earth's surface temperatures. Global warming could result in environmental problems such as rising sea levels caused by melting glaciers and sea ice and shifting of Earth's climatic zones. Question number 1. Electromagnetic energy that reaches Earth from the sun is called insolation, conduction, specific heat, or terrestrial radiation. Question number 4. If dust particles are added to the atmosphere, the amount of insulation reaching the ground will probably decrease, increase, stay the same, or increase then decrease. Number 5. Ozone is more important to life on Earth because ozone cools refrigerators and air conditioners, absorbs energy that is radiated by Earth, absorbs harmful ultraviolet radiation, or destroys excess atmospheric carbon dioxide. Number 6. Which form of electromagnetic energy is radiated from Earth's surface with the greatest intensity? X-rays, infrared rays, ultraviolet rays, or visible light rays? Number 7. In land areas of equal size located at the same latitude, the most solar radiation would probably be reflected by a snowfield, sandy desert, grassy field, or forest. Variation of insolation. Insolation varies from place to place on Earth's surface. It also varies in any given place over the course of a year. Insolation can vary in 2 general ways: by intensity and by duration. Variation in intensity and angle of insolation. The rate at which solar energy is received by a given area per unit time is the intensity of insolation. Intensity of insolation can be measured in joules per square meter per second. The intensity of insolation received at a particular area of Earth's surface varies for several reasons because of the angle of incidence. When insolation strikes a surface at an angle of 90 degrees or perpendicular, it has maximum intensity because the insolation is concentrated in the smallest possible area. As the angle of incidence decreases from 90 degrees towards 0 degrees, the same amount of insolation is spread out over greater and greater areas, as shown in figure 6.5. Therefore, at smaller angles of incidence, the intensity of insolation decreases the heating effect. Effective Earth shape and thickness of the atmosphere. The sun's energy reaches Earth as a bundle of parallel rays. If Earth were flat and positioned perpendicular to these rays, the intensity of insolation would be the same everywhere on Earth's surface. However, Earth is shaped like a sphere. As a result, at any given time, there's just one place where insolation arrives perpendicular to Earth's surface. At other places on Earth, the angle of incidence is less than 90 degrees. Generally, for each of the degree of latitude north or south of the place where insolation is perpendicular to Earth's surface, the angle of incidence is 1 degree less. The thickness of Earth's atmosphere, which the sun's rays have to pass through to each Earth's surface, varies greatly during the day and year, which changes in latitude. When the sun is straight, when the sun is straight overhead at a 90-degree angle of insolation, the intensity of the insolation is about 80 times stronger when the sun is on the horizon at a 0 angle of insolation. This is due partly to the changes in the thickness of the atmosphere, and the sun's rays must pass through. It's minty chocolate.
Okay.
The more atmosphere the sun's rays may pass through, the greater the absorption, refraction, and scattering of the rays, and less the transmission of the rays to Earth's surface. Effective latitude.
I like chocolate.
The intensity of insolation is greatest at the equator at each equinox and decreases with increasing latitude. As shown in figure 6.6, insolation is perpendicular to Earth's surface at the equator at the time of equinox. The spring equinox is March 21st and the fall equinox is September 23rd. On the first day of summer in the northern hemisphere, insolation is perpendicular to Earth's surface at 23.5 north latitude. The intensity of insolation is at a maximum this latitude. On the first day of winter in the northern hemisphere, insolation is perpendicular to Earth's surface at 23.5 degrees south latitude. The intensity of insolation is at its maximum at this latitude, the Tropic of Capricorn. The effect of seasonal change. As Earth travels its yearly orbit around the Sun, the angle of incidence for insolation at any given latitude varies with the seasons. As shown in figure 6.7, the lowest angle of incidence is 42 degrees north latitude, occurs at winter solstice, and the highest angle at the summer solstice. As shown in table 6.2. The angle of incidence for insolation decreases by 1 degree for each degree of latitude away from the point of perpendicular insolation. Effective time of day. On any given day, the altitude of the sun varies from 0 at sunrise to a maximum at apparent solar noon, and back to 0 again at sunset. In a similar way, the angle of incidence and the intensity of insolation also vary during the day, as shown in figure 6.8. The maximum angle and intensity occur at solar noon. Variation in duration of insolation. The length of time that insolation is received each day, or the time between sunrise and sunset, is called duration, or of insolation. The duration of insolation at a given location corresponds to the number of hours the sun is visible each day, as shown in table 6.2. The duration of insolation varies with altitude with the seasons, and in the continental United States, duration of insolation is longest on the summer solstice and shortest at the winter solstice. On the equinoxes, the average duration of insolation is 12 hours. Effects of latitude and season. A review of table 6.2 will reveal how duration of insolation varies with latitude